Imagine, a flash of light leaves Earth, headed for the nearest star. 4 years. For unbroken years of travel, just to reach our cosmic doorstep. To cross the entire Milky Way? 100,000 years. Longer than all recorded human history. Physics, as we know it, locks us in a cage built from distance and time. But what if that cage isn't permanent? What if we don't outrun physics, but literally bend it? Our fastest machines offer an illusion of speed. A rocket blasting off Earth feels dramatic. Yet, against the universe, that motion barely counts. What feels fast to us is nearly motionless to space itself. Human intuition wasn't built for interstellar distances. Light sets the benchmark, nearly 700 million miles per hour. Nothing known can outrun it. Still, a light beam takes over 4 continuous years to reach the nearest star beyond our Sun. That's the closest destination. Cross the Milky Way, and the numbers lose all meaning, 100,000 years. Space isn't just big, it's structured to resist crossing. We've pushed technology to its limits. The Voyager probes, launched in the late 1970s, have traveled for nearly half a century. Now farther from Earth than any human-made object, they are still barely on the doorstep of interstellar space. Their galactic journey has barely begun. If aimed at the nearest star, Voyager would need tens of thousands of years. This is a consequence of physics. Every propulsion system we've built follows one rule: to move forward, something must be thrown backward. The math is unforgiving: faster travel demands more energy. More energy means more mass. More mass means harder to accelerate. Fuel pushes fuel. This feedback loop is the rocket equation, feared and inescapable. Even extreme ideas like fusion or antimatter hit the same wall. Near light speed, energy demands explode. Equations demand infinite energy. Infinite means impossible. This is a structural feature of reality. Time makes everything worse. As objects move faster, time slows down for them relative to the rest of the universe. This has been measured. At relativistic speeds, years on board could mean decades or centuries on Earth. Exploration becomes separation. Acceleration also imposes biological limits. Human bodies tolerate only modest forces. Sustained acceleration for relativistic speeds would be fatal. Organs shift. Biology draws its hard lines. This leaves grim choices: crawl for millennia, send generation ships, or abandon human travel. None satisfy our deeper drive. This problem isn't just exploration, it's survival. Earth is fragile, an oasis in a hostile cosmos. Other solar system worlds are lethal. Thousands of exoplanets offer hope, but are unreachable. The nearest habitable one is just over 4 light-years away. Reaching it with current tech would take longer than modern humans have existed. These distances don't just test patience, they erase relevance. This is the true prison. Not fuel limits, not engine design, but distance itself. The universe denies us the means to visit extraordinary worlds. Knowledge without access. Discovery without arrival. Unless our understanding of motion is incomplete. Unless the mistake has always been assuming the ship must cross the distance at all. That quiet realization marks the end of everything we thought knew about travel. It's the beginning of a radically different way of thinking about movement. The barrier isn't technological, it was discovered over a century ago. In 1905, Albert Einstein revealed something deeply unsettling: space and time were not separate. They were spacetime. And once joined, they imposed a limit nothing with mass could ever overcome: the speed of light. This isn't just the fastest thing we know, it's the maximum speed at which cause and effect can propagate through spacetime. It's baked into reality. Before Einstein, time was universal, space a fixed stage. He destroyed that, demonstrating time depends on motion, and motion depends on time. Move faster through space, move slower through time. It's measurable. Near light speed, energy demands explode, requiring infinite energy. Infinite means forbidden. This makes light speed a structural limit. Particle accelerators confirm it daily. Subatomic particles never cross the light barrier. Light speed is not negotiable for objects with mass moving through space. This cast a long shadow over faster-than-light travel. For decades, it was deemed impossible, a violation of causality. Reality doesn't tolerate contradiction. Time dilation meant explorers would return as temporal refugees. Not a solution for a species, it fragments history. Einstein's equations seemed absolute. Physicists searched for loopholes. None mattered. Every proposal relied on accelerating mass through spacetime, and spacetime enforced its limit without mercy. The wall held firm. Then, slowly, the perspective shifted. Einstein's theory doesn't say nothing can move faster than light. It says nothing with mass can move faster than light through space. That distinction is crucial. The equations place no restriction on how fast space itself can change. We already know space can change very quickly. On larger scales, the universe is expanding. Distant galaxies aren't flying away, the space between them is stretching, carrying them away faster than light can cross the gap. This doesn't violate relativity because locally, nothing outruns light. The geometry itself evolves. The universe already permits faster-than-light separation. This realization cracked the wall. If space itself can expand faster than light, perhaps it can also contract. If distance isn't fixed, but a property of geometry, then changing geometry changes distance. You don't need to outrun the universe if you can reshape it. This reframing changed everything. Instead of asking how to push a spacecraft harder, physicists began asking how to manipulate spacetime directly. Gravity already does this naturally. Massive objects bend spacetime inward. Planets orbit by following curved paths through spacetime. The equations describing gravity don't limit how spacetime can curve, only how much energy and pressure are required. That unsettling realization meant the speed limit wasn't a wall after all. It was a rule about motion within spacetime, not a rule about spacetime itself. The barrier remained intact, but the possibility of stepping around it emerged. This reframing changed everything. Instead of asking how to push a spacecraft harder, physicists began asking how to manipulate spacetime directly. This opened entirely new territory. For years, these revolutionary ideas lived quietly in mathematics, dismissed as interesting but unrealizable curiosities. Then, someone decided to take them seriously, not as fantasy, but as a blueprint for engineering. This decision marked the moment faster-than-light travel re-entered physics, not as a violation of Einstein's work, but as a profound consequence of it. Einstein's theory didn't lock the universe into immobility. It described its architecture. And within that architecture, corridors appeared where outrunning light wasn't necessary at all. The question shifted, not how fast can a ship go, but how can space itself be shaped? Distance was no longer a fixed obstacle, but something adjustable, like folding a map instead of walking across it. In the mid-1990s, a physicist named Miguel Alcubierre pushed Einstein's equations in this new direction. Using the same mathematics that describes black holes and the expanding universe, he asked a simple, radical question: could spacetime itself be arranged to carry an object faster than light, without the object locally ever moving faster than light? The equations answered yes. What emerged was not a traditional vehicle, but a moving bubble of spacetime. Inside this bubble, space would remain flat and calm, indistinguishable from Earth. Time would flow normally. Physics would behave as expected. All the drama would unfold outside. In front of the bubble, spacetime would be compressed, distances shrinking, pulling the destination closer. Behind it, spacetime would expand, stretching the space already traversed. This imbalance creates motion, not by pushing the ship forward, but by moving spacetime itself. The bubble would ride this distortion like a wave, carried forward without the ship inside ever accelerating. The spacecraft wouldn't cross the distance would be rearranged around it. Think of it like a conveyor belt. Stand still on the belt, and you still move across the room. Or a surfer riding an ocean wave. The surfer isn't swimming faster than the water, they're carried by the wave's motion. Similarly, a warp bubble carries a spacecraft without the craft locally breaking any speed limit. This distinction is critical. Einstein's speed limit applies to objects moving through spacetime. The warp concept avoids that entirely. Locally, nothing moves faster than light. No particle within the bubble violates relativity. No signal outruns causality. From the ship's perspective, it's at rest, floating in ordinary spacetime while the universe reshapes around it. Mathematically, this changes everything. Because the ship never accelerates, the usual relativistic penalties vanish. No time dilation separating the crew from Earth's timeline. No length contraction distorting their surroundings. No requirement for infinite energy. The nightmare scenarios of near light-speed travel simply disappear. From inside the bubble, the experience would feel almost boring. You could walk through the cabin, eat, sleep, and wake up without anything feeling unusual. Your clocks would tick at the same rate as clocks back home. You could travel to a nearby star and return within the same historical era. That alone makes the idea revolutionary. Warp travel offers speed without temporal exile. Distance collapses without tearing you away from your civilization. Acceleration is also removed from the equation. Conventional propulsion requires prolonged, crushing acceleration. Inside a warp bubble, there is no acceleration at all. The ship doesn't feel pushed. Occupants experience no inertial forces. Even a sudden change in effective speed would be imperceptible. From an engineering perspective, this removes one of the most brutal barriers to interstellar travel. To an outside observer, however, the warp bubble would appear deeply strange. Light passing near strongly curved spacetime doesn't behave normally. Ahead of the bubble, light could be compressed to higher energies, behind it, stretched to lower. The ship might appear distorted, dimmed, shifted in color, or even partially invisible. It would look less like a fast-moving object and more like a traveling disturbance in the structure of space itself. And that disturbance could move extraordinarily fast. In Alcubierre's original solution, there was no upper limit on effective speed. 10 times the speed of light was trivial. 100 times was allowed. 1,000 times still satisfied the equations, because nothing inside the bubble was breaking the light barrier. The speed limit no longer applied in the usual way. This stunned physicists. The equations weren't speculative, they were standard general relativity, the same framework that accurately predicts black holes and gravitational waves. There were no illegal steps, no broken assumptions. The solution was uncomfortable, but valid. It didn't say warp travel was easy, it said it was permitted. For years, the idea remained mostly theoretical, discussed cautiously and often dismissed as impractical. The energy requirements looked catastrophic. The materials appeared exotic. But something fundamental had changed. Faster-than-light travel was no longer ruled out by physics itself. It had crossed a critical threshold, moving from impossible to allowed, but extreme. History shows technologies often exist in this uncomfortable middle ground. Flight was allowed long before engines were powerful enough. Nuclear energy was mathematically possible before reactors existed. Warp travel had entered that same category. The universe, by its own rules, didn't forbid this motion. It simply demanded unusual conditions. The problem was no longer philosophical, it was technical. And technical problems, with enough ingenuity, have a way of being attacked from unexpected angles. But this flexibility came at a price. Warp bubbles required spacetime to be curved in highly unusual ways. Producing those curvatures demanded energy configurations unlike anything we routinely handle. The equations allowed it, but they didn't make it convenient. And that led directly to the most difficult challenge of all: if spacetime could be shaped like this, what kind of energy would it take to actually do it? That question would determine whether warp travel remained a mathematical curiosity or the first step toward leaving our cosmic prison behind. The warp concept survived because the mathematics allowed it. But mathematics is only the first gate. Beyond it waited the real challenge, one far less forgiving than equations on a page. If spacetime could be shaped into a moving bubble, then something had to supply the energy to bend spacetime in such an unnatural way. When physicists followed that requirement to its conclusion, they ran straight into the most serious obstacle: energy. Einstein's equations are clear. Spacetime doesn't curve on its own. It responds to energy and pressure. Ordinary matter bends spacetime inward, creating gravity. This inward curvature is familiar. A warp bubble, however, demands the opposite behavior: to shrink space in front and stretch it behind. Spacetime must curve outward in certain regions. That requires negative energy density. Not antimatter, which still has positive energy. Something stranger, something that pushes spacetime outward instead of pulling it inward. In simple terms, normal energy attracts. Negative energy repels. At first, this seemed fatal. No known substance behaves this way on large scales. Every form of matter and energy we interact with contributes positive energy. Negative energy appeared only as a mathematical possibility, allowed by equations but seemingly absent from the real universe. Then physicists calculated how much of this exotic energy would be required. The early answers were devastating. To create a warp bubble large enough for even a small spacecraft, the equations demanded an amount of negative energy comparable to the mass energy of an entire planet, in some models, as much as Jupiter. That mass would need to be converted entirely into usable energy and arranged with near-perfect precision around the bubble. This was not merely difficult, it was absurd. Even imagining such resources strained credibility. For many researchers, this seemed to close the case. Warp drives were allowed by physics, but demanded ingredients the universe did not appear willing to provide. For a time, interest faded. But the story did not end there, because physics rarely does. The next breakthrough came not from exotic stars or hypothetical particles, but from empty space itself. According to quantum theory, the vacuum is not truly empty. It is alive with fluctuations, tiny bursts of energy where particles briefly appear and vanish. Normally, these fluctuations cancel out, leaving no observable effect. Space looks empty because the chaos balances itself. Under certain conditions, however, that balance can be disturbed. When two uncharged metal plates are placed extremely close together, the quantum fluctuations between them are restricted. Some wavelengths of virtual particles cannot exist in the narrow gap. Outside the plates, all wavelengths remain allowed. This imbalance creates a small pressure difference, pushing the plates together. This phenomenon is known as the Casimir effect. What makes it remarkable is not the force itself, which is tiny, but what it represents. The space between the plates contains less energy than the surrounding vacuum, relative to its environment. That region has negative energy density. Not hypothetical, not theoretical, measured, verified, real. This discovery changed the conversation. Negative energy did exist in nature. Not in vast quantities, not in convenient forms, but undeniably present. The universe was not forbidding negative energy outright. It was allowing it in carefully controlled, microscopic amounts. This raised a dangerous question: if negative energy can exist locally and briefly, could it be engineered? Could many small regions be arranged together? Could geometry reduce how much is required? Could clever design replace brute force? Physicists returned to the warp equations with renewed focus. And what they found was encouraging. The energy requirement was not fixed. It depended heavily on the shape and structure of the warp bubble. Early models used simple geometries because they made the math manageable: thick bubble walls, sharp transitions, clean symmetry. But simplicity in mathematics often hides inefficiency in physics. By reshaping the bubble, thinning its walls, smoothing its boundaries, allowing dynamic oscillations instead of static fields, researchers discovered that the required negative energy dropped dramatically, not by small margins, but by orders of magnitude. Each refinement reduced the demand further. The problem shifted. Instead of needing planet-sized quantities of negative energy, some optimized models reduced the requirement to something closer to the mass of a spacecraft. Still exotic, still unavailable, but no longer cosmically impossible. This distinction matters. Physics doesn't care whether something is easy. It only cares whether it is forbidden. And the equations never forbade warp bubbles. They simply demanded conditions far beyond our current reach. The Casimir effect offered a proof of principle. Negative energy density could be created artificially, even if only at microscopic scales. The challenge was scaling it up. And scaling in physics is never trivial. Casimir forces weaken rapidly with distance. Move the plates slightly farther apart, and the effect collapses. What works at nanometers does not automatically work at meters. This is where the difficulty deepens. Warp drives do not just require large amounts of energy. They require precise control over how that energy is distributed across spacetime. Tiny errors could destabilize the bubble. Uneven energy gradients could produce intense radiation or gravitational effects. The margin for error is unforgiving. And yet the door never closed. Every time researchers revisited the equations, the same conclusion emerged. No fundamental law prohibited the configuration. No principle of physics declared it impossible. The universe did not push back with a hard stop. It merely demanded extreme precision and unfamiliar energy states. This is a dangerous place for skepticism to stand. History shows that once something moves from impossible to merely difficult, progress tends to follow. Warp energy now occupied that same space. The problem was no longer philosophical. It was experimental. Could negative energy be generated in larger quantities? Could vacuum fluctuations be amplified or arranged coherently? Could spacetime be coaxed into the required shape without tearing itself apart? These were no longer abstract questions. They were engineering challenges waiting for laboratories, instruments, and funding. Slowly, quietly, those laboratories began to appear. The energy barrier remained the greatest obstacle. But it was no longer an absolute wall. It had cracks, narrow ones, but real. Through those cracks, a new idea emerged. One that would push warp drive research out of equations and into physical experiments. If negative energy existed, even in tiny amounts, perhaps spacetime itself could be nudged, gently at first, then more deliberately. The question was no longer whether warp travel violated the laws of physics. The question became whether humanity could ever learn to handle the strange, subtle energy hidden inside empty space well enough to shape spacetime on purpose. And that question would soon be tested, not in theory, but in the lab. For decades, warp drives lived comfortably on paper. They existed in equations, simulations, and speculative discussions, safely isolated from the messy constraints of reality. The mathematics said spacetime could be shaped this way. But mathematics alone does not move spacecraft. To cross the next threshold, warp physics needed something far more dangerous than theory. It needed experimental evidence. That transition began quietly, far from science fiction headlines, inside research labs focused on questions most people never think about. How does empty space behave? Can vacuum energy be manipulated? Are there measurable ways to bend spacetime without massive objects like planets or stars? One of the scientists drawn to these questions was Harold White, a physicist working at NASA's Johnson Space Center. White wasn't trying to build a warp ship. He was studying propulsion physics at the edges of what was considered respectable science, exploring whether exotic concepts might one day offer alternatives to conventional rockets. White understood the skepticism surrounding warp drives. He shared it. But he also recognized something important. Alcubierre's equations were not fantasy. They were valid solutions to Einstein's field equations. If they were valid, then spacetime itself did not forbid warp-like geometries. The real question was scale. Could even a tiny version of a warp bubble be created? White and his team focused on the only known phenomenon that reliably produces negative energy density, the Casimir effect. In controlled laboratory conditions, they worked with precisely arranged plates and electromagnetic fields, measuring extremely small forces with extraordinary sensitivity. These experiments were not designed to move anything. They were designed to observe whether spacetime itself responded, even faintly, to engineered vacuum energy differences. At first, the goal was modest: measure, confirm, eliminate noise. Then something unexpected appeared in the data. Under specific configurations, sensors detected minor distortions consistent with warped spacetime geometry. Not gravity from mass. Not electromagnetic interference. A subtle, repeatable signal matching what theoretical models predicted for a microscopic warp-like structure. In essence, a warp bubble had appeared. Not large enough to move a grain of sand, not powerful enough to transport anything, but real. This was a critical moment. For the first time, warp drive geometry was no longer confined to equations. A structure resembling Alcubierre's spacetime distortion had been generated, measured, and reproduced in a laboratory. The scale was nanoscopic, millions of times smaller than anything useful for propulsion, but the implication was profound. Spacetime could be shaped deliberately. White's team repeated the experiments, refined their instrumentation, and verified that the effect appeared only under specific conditions predicted by theory. When those conditions changed, the effect vanished. This correlation mattered. It suggested the phenomenon was not an artifact or coincidence, but a real physical response. Skepticism followed immediately, as it should. Extraordinary claims demand extraordinary scrutiny. Other physicists proposed alternative explanations: electromagnetic artifacts, thermal noise, quantum measurement errors. White's group addressed these systematically, isolating variables, calibrating sensors, and ruling out known sources of interference. While debate continues, the core result remains difficult to dismiss outright. A spacetime distortion consistent with warp geometry had been observed. This shifted warp drive research into an entirely new category. It was no longer purely speculative. It had entered the early experimental phase, the most fragile and controversial stage of any revolutionary technology. NASA responded carefully. Public statements emphasized caution, stressing that the work was preliminary and that practical applications remained far in the future. Privately, however, funding increased. More sophisticated equipment was approved. Additional researchers were brought in. The work expanded from a single curiosity into a structured research program. The psychological barrier had been breached. Once a phenomenon is observed in the lab, even at microscopic scale, it becomes far harder to dismiss. Engineers begin asking how to amplify it. Physicists begin refining models. Grant proposals become easier to justify. The idea stops being laughed out of rooms and starts being argued about seriously. Warp physics crossed that line. The implications extended far beyond propulsion. If spacetime could be warped deliberately at small scales, it suggested new ways of thinking about gravity, vacuum energy, and the structure of reality itself. Warp research began overlapping with quantum field theory, condensed matter physics, and advanced material science. And it raised an unsettling thought: if humans can create microscopic warp effects with crude, early technology, what might a civilization centuries or millennia ahead of us be capable of? This question inspired an entirely different line of inquiry. Warp bubbles distort spacetime. Distorting spacetime produces gravitational waves. These ripples propagate outward at light speed, carrying information about the motion and geometry of the source that created them. We have already detected gravitational waves from black hole mergers and neutron star collisions, events occurring billions of light-years away. If a large-scale warp drive were operating anywhere in the galaxy, it would not be silent. It would leave a signature. Physicists began modeling what a moving warp bubble would look like to gravitational wave detectors. The patterns were distinctive, unlike natural astrophysical events. A warp bubble would produce asymmetrical, sustained distortions, not the brief bursts associated with cosmic collisions. In other words, warp drives would leave fingerprints. This led to a radical idea. Instead of waiting to build a full-scale warp drive ourselves, what if we could detect evidence that someone else already had? Not by seeing their ships, but by listening to the universe itself. Gravitational wave observatories have only existed for a short time. Humanity detected its first confirmed gravitational wave in 2015. Since then, our instruments have grown more sensitive, but they are still crude compared to what future detectors will achieve. The universe has been speaking for billions of years. We have only just learned how to listen. If an advanced civilization were using warp drives within a few billion light-years, their activity could, in principle, be detectable. Even a single unshielded warp transit might leave a ripple passing through Earth long after the event occurred. Such a detection would be historic. It would instantly confirm that faster-than-light travel is physically achievable. It would provide real-world data on warp bubble geometry, energy distribution, and motion. It would transform warp research overnight, from speculative engineering into reverse engineering. No such signal has been confirmed yet, but the absence of evidence means little at this stage. Our detectors are young. Our search methods are limited. And warp-capable civilizations, if they exist, may be rare, cautious, or far away. Still, the idea changed how scientists thought about warp research. The universe itself became a potential laboratory. Back on Earth, experimental work continued. Researchers explored whether different geometries could amplify vacuum effects. Whether metamaterials could shape electromagnetic fields to influence spacetime indirectly. Whether quantum coherence might allow multiple small negative energy regions to reinforce each other. Progress was slow, incremental, and frustrating. But that is how every breakthrough begins. Flight did not leap from ground to jetliners in a single step. Nuclear energy did not appear fully formed. Each began with weak effects, partial demonstrations, and experiments that barely worked at all. Warp physics had reached that stage. The lab-scale warp bubble did not mean starships were around the corner, but it meant the universe had answered a critical question. When asked whether spacetime could be bent deliberately using engineered energy configurations, reality did not say no. It whispered yes, very quietly. And that whisper was enough to change everything. The question now was not whether warp bubbles could exist, but whether they could be scaled, stabilized, and controlled. Whether nanoscopic distortions could grow into meter-scale structures. Whether fleeting effects could be sustained. Whether spacetime could be shaped reliably enough to trust human lives inside it. Those questions would define the next phase of research. Warp travel had left the realm of pure theory. It had entered the long, uncertain road toward engineering. And once that road begins, history suggests it rarely ends where it started. At this point, the question is no longer whether faster-than-light travel belongs purely to science fiction. The equations allow it. Experiments hint at it. The universe so far has not closed the door. The real uncertainty lies somewhere deeper, in what happens next, after theory meets engineering. And engineering begins to push back against the limits of reality. Because building a warp drive is not a single problem. It is a cascade of problems. Each one unlocking the next. Each one demanding precision at levels humanity has rarely attempted before. Scaling is the first and most unforgiving challenge. Creating a microscopic spacetime distortion in a laboratory is one thing. Expanding that distortion to the size of a vehicle, maintaining it for hours or days, and keeping it stable under changing conditions is something entirely different. Physics does not scale politely. Effects that behave predictably at nanometers often collapse at meters. Forces weaken. Instabilities grow. Control becomes exponentially harder. Warp bubbles are especially sensitive. Their boundaries represent sharp transitions in spacetime curvature. Any unevenness in energy distribution could destabilize the bubble, collapse it, or generate extreme radiation at its edges. Unlike conventional engines, failure modes are poorly understood. When spacetime itself is the system you are manipulating, mistakes are not easily corrected. Then there is navigation. Moving without acceleration sounds simple until you ask how steering works. A warp bubble does not push against space. It reshapes it. Changing direction means reshaping spacetime asymmetrically, altering the geometry of contraction and expansion while the bubble is already in motion. That requires real-time control of energy distributions across spacetime itself, guided by sensors that must operate through extreme curvature. Seeing where you're going may not even be possible. Light behaves unpredictably around strong spacetime distortions. Forward-facing views may be compressed beyond visibility. Rearward views may stretch into wavelengths no human eye can detect. A warp-driven spacecraft could travel blind, relying entirely on instruments, predictive models, and navigation systems that must remain accurate even when normal assumptions about distance and time break down. Communication introduces another complication. Signals trying to leave or enter a warp bubble may not cross its boundary cleanly. The same spacetime distortion that protects the interior could isolate it. That means a ship in transit might be completely cut off, unable to send or receive messages until it exits warp. Missions would require autonomy at a level far beyond current spacecraft, with crews and systems trusted to operate independently for extended periods. Energy generation remains the largest unresolved obstacle. Even with optimized geometries, warp drives demand enormous power delivered with extraordinary precision. Fusion may eventually provide the raw output, but raw output is not enough. The challenge lies in shaping that energy into the exact distributions required to bend spacetime without tearing it apart. Power surges, fluctuations, or asymmetries could have catastrophic consequences. And yet, none of these challenges represent hard stops. They are engineering problems, not prohibitions. That distinction matters more than it ever has. History shows that once a technology crosses from forbidden to merely difficult, progress tends to accelerate. Flight faced stability issues. Nuclear power faced containment problems. Spaceflight faced guidance, propulsion, and life support challenges that once seemed insurmountable. Each was solved incrementally, often in ways no one initially predicted. Warp technology appears to be entering that same phase. But its consequences extend far beyond propulsion. If warp travel becomes possible, even at modest speeds, it reshapes humanity's future overnight. The nearest star systems stop being abstract points of light and become reachable destinations. Worlds identified by telescopes become places we can visit, study, and potentially settle. Interstellar exploration shifts from generational fantasy to strategic planning. This transforms survival itself. Humanity exists today as a single-point failure species. One planet, one biosphere, one fragile equilibrium. Warp travel changes that equation. With access to nearby star systems, humanity could spread, diversify, and reduce existential risk. No single disaster could end the entire species. It also transforms economics. Resources locked away in distant systems suddenly become accessible. Rare elements, vast energy reserves, and entire new environments enter the realm of possibility. The scale of available resources expands beyond anything Earth alone can provide. Entire industries would emerge around interstellar logistics, construction, and exploration. Science would change just as radically. Instead of studying stars, planets, and black holes from afar, we could approach them directly. We could observe stellar interiors, study alien ecosystems, test theories of gravity near extreme objects, and answer questions that have remained open for centuries. Astronomy would become a hands-on science. Then there is the most profound possibility of all, contact. If intelligent life exists anywhere within reach, warp travel makes discovery almost inevitable. Not through slow radio conversations stretched across generations, but through direct exploration. The first confirmed evidence of extraterrestrial intelligence would redefine humanity's understanding of itself, its place in the universe, and its future trajectory. Of course, risk grows alongside opportunity. Warp technology would be powerful, potentially dangerous. A civilization capable of manipulating spacetime could also weaponize it. Political, ethical, and military implications would follow quickly. Who controls access? Who decides where humans can go? How are new worlds protected from exploitation? These questions will not wait politely for answers. And there are deeper risks we barely understand. Repeated warp travel might have long-term effects on spacetime itself. Distortions could accumulate. Quantum fields could be disturbed in ways we do not yet know how to predict. The universe may tolerate occasional bending, but react badly to frequent manipulation. We simply do not know. Causality remains a looming concern. While warp travel appears to avoid many paradoxes associated with near-light-speed motion, faster-than-light effects still brush against deep questions about time and order. It is possible that unknown mechanisms protect reality from paradox, limiting what warp drives can actually do. Or it is possible that entirely new physics emerges when spacetime is manipulated at scale. Either outcome would revolutionize science. And that brings us to the final uncertainty. How close are we really? Optimists argue that if current trends continue, early prototypes could appear within decades. Pessimists insist the obstacles are too deep, the scaling too severe, the unknowns too dangerous. History suggests both sides are usually wrong. Breakthroughs tend to arrive suddenly, triggered by discoveries no one was actively searching for. A new way to amplify vacuum energy. A new material that stabilizes spacetime gradients. A deeper understanding of dark energy or quantum gravity. Any one of these could collapse timelines overnight, or progress could stall for generations. But something important has already happened. Warp travel has crossed a threshold. It is no longer mythology. It is no longer dismissed outright. It lives in laboratories, simulations, and serious research programs. That alone marks a turning point in human history. The universe once appeared to imprison us within light-speed walls. Now those walls look less like barriers and more like rules with exceptions, structures with seams, limits that can be approached from unexpected angles. We may still be far from building a working warp ship, but for the first time, we know what we're aiming for. And that changes everything. Because once humanity knows a path exists, even a narrow one, curiosity and persistence tend to do the rest. The same instincts that carried us across continents and oceans are now aimed outward, toward the stars that have watched us evolve in silence. Whether warp drives arrive in decades or centuries, the direction is set. The universe is no longer just something we observe. It is something we are learning, slowly and carefully, how to move. And when you finally journey beyond the familiar, remember that first whisper from the void, the one that dared to say, yes. Remember the 699,999,999 years that could pass before we even know how to begin.